Welcome to Deep Dive Lab, where we break down and dissect cutting-edge scientific research. From advanced biomedical technologies to breakthroughs in AI, material science, chemistry, and physics, all told as compelling, easy-to-follow stories. Today, we are taking a deep dive into something you probably interacted with this very week, like completely on autopilot. Picture this. You're standing at the gas pump.
Right, just staring into space.
Yeah, exactly. You grab the heavy handle, select your grade, and right there next to the button is a little yellow sticker. May contain up to 10% ethanol, or maybe 15%. You've seen it 1,000 times, and you probably completely ignore it. But what is that plant juice actually doing inside your engine?
I mean, most of us just assume it's a simple, harmless additive, right? Like a little drop of farm-grown goodness to stretch the fossil fuel further and, maybe help the environment a bit.
Right. Here's a strange question, though. Why does adding a seemingly simple, renewable plant-based alcohol to our gasoline cause cars to run cooler but burn hotter, reduce smog but increase toxins, and spark one of the most intense environmental tug-of-wars in modern science?
It really is a paradox. On the surface, ethanol is marketed as the ultimate green solution. But when you look at the molecular level and you observe what it actually does inside a high-pressure combustion chamber, it turns out this simple alcohol leads a bizarre chemical double life.
Okay, let's unpack this. Because
Okay.
to understand the chemistry happening at the pump today, we actually have to rewind the clock to the dawn of the automobile.
Right. The first thing to understand is that putting ethanol in engines isn't some new idea. It was originally viewed as the perfect green drop-in fuel. If we go back to the pioneers of the internal combustion engine, Nicholas Otto and Henry Ford were actually designing engines to run on alcohol.
Oh, really?
Yeah. Henry Ford's famous Model T was remarkably versatile. It was essentially a flexible fuel vehicle.
So it wasn't just gasoline.
No, not at all. The carburetor had an adjustable jet that allowed the driver to manually tune the air-fuel mixture, meaning it could run on pure ethanol, pure gasoline, or a mix of both.
So, like, the farmer in 1908 could theoretically grow their own fuel, distill it, and pour it straight into the tank.
Exactly.
But obviously, gasoline took over. I imagine that just came down to pure energy density and the economics of striking oil.
Precisely. Gasoline packed a lot more energy per gallon and became incredibly cheap to extract and refine.
Cheap and easy.
Right. But as decades passed and engines got more powerful, with higher compression ratios, they ran into a severe mechanical issue. They called it knocking.
Oh, that pinging sound you hear sometimes.
Yeah, exactly. It's when fuel detonates too early in the cylinder due to pressure and heat. Before the spark plug even fires, it can literally tear an engine apart.
Yikes.
So to stop that, the industry needed octane boosters to stabilize the fuel, and they started adding tetraethyl lead.
Which solved the mechanical problem, but created a catastrophic global public health disaster, pumping a known neurotoxin into the atmosphere of every major city.
A massive disaster. So we eventually phased out lead and replaced it with a chemical called MTBE, methyl tert butyl ether.
Okay.
It boosted octane and helped the fuel burn cleaner, but MTBE is highly soluble in water.
Which I'm guessing is a bad thing for underground storage tanks.
Oh yeah. When those gas station tanks inevitably leaked, the MTBE moved rapidly through the soil, contaminating groundwater and drinking supplies with this foul-tasting, potentially carcinogenic chemical.
So by the time the oil shocks of the 1970s hit, and later the stricter Clean Air Act amendments, the industry was desperate. And suddenly, ethanol looks like a knight in shining armor.
Exactly.
I mean, it boosts octane, it's a renewable resource grown in the Midwest, and it replaces toxic synthetic chemicals that seem flawless.
On paper, yes. But when researchers began deeply testing modern, highly tuned engines on these new ethanol blends, the results were totally baffling.
Wait, if this is fundamentally the exact same chemical compound, like ethyl alcohol that you'd find in a cocktail, why is it acting like a Jekyll and Hyde inside an engine? How can a fuel be heralded as green but also actively melt engine components?
Well, the answer lies entirely in ethanol's unique molecular structure. It's a short-chain alcohol, so just 2 carbon atoms, 6 hydrogens, and 1 crucial oxygen atom.
Just that tiny difference.
Yeah, how those molecules bond together, and specifically how they interact with heat, changes the physics of everything inside the engine.
Okay, so how did scientists figure this out? This is where the story gets interesting, I assume.
It does, because they aren't just, looking at the tailpipe exhaust anymore.
Right.
No, the methodology has advanced incredibly. Let's look at foundational research by mechanical engineers like Stein and his colleagues, alongside a major 2025 narrative review published in the journal Helion.
What are they actually doing in the lab?
They use optical and pressure-based diagnostics. They literally build specialized engines with transparent quartz cylinders.
Wait, see-through engine blocks.
Exactly. They fire lasers through the combustion chamber and use ultra-high-speed cameras to watch the flame front propagate in real time.
So they are literally watching the chemistry of the explosion unfold microsecond by microsecond.
Yes.
What does that actually look like when you swap gasoline for ethanol?
Well, the first major finding centers on performance. Ethanol has a massive research octane number, or ON. It sits around 108, which is substantially higher than standard premium gasoline.
Meaning it strongly resists that premature detonation or knocking we talked about.
Right, but the truly fascinating mechanism is ethanol's remarkably high latent heat of vaporization.
Okay, let's break down the mechanism of latent heat. When a liquid turns into a gas, it requires a significant amount of thermal energy to break the intermolecular bonds.
Yes, exactly. Because ethanol molecules are held together by strong hydrogen bonds, breaking them apart to turn the liquid into a vapor absorbs a massive amount of heat from the surrounding environment. So, as the fuel injector sprays ethanol into the intake port, or the cylinder, the ethanol literally sucks the thermal energy right out of the incoming air.
Oh, wow. So it's basically like the engine is sweating.
How do you mean?
Like when we sweat, the water evaporates off our skin, absorbing body heat and cooling us down. The ethanol absorbs the heat to vaporize, which actively refrigerates the engine's intake charge, making the air denser and letting the engine work much harder without knocking.
That is a brilliant analogy. Yes, the engine is effectively sweating from the inside out.
That's wild.
It is. And because the intake air is suddenly much cooler and denser, the engine's computer can advance the ignition timing, it can compress that air-fuel mixture harder, and extract more mechanical work.
Wow.
Yeah, the Helion review confirmed that low to mid-level blends, up to about 20% ethanol, can increase brake power by about 5% and torque by 3% compared to neat gasoline.
So that's the Dr. Jekyll side of the fuel.
Yeah.
Better power, cooler internal temperatures, higher octane. But given the chemistry we just discussed, I can see the twist coming.
Yeah, here is the wow moment, often referred to as the emissions paradox. Because ethanol has that extra oxygen atom built right into its molecular structure, it physically brings its own oxygen to the fire.
Promoting a faster, much more complete combustion.
Exactly. The studies found that shifting from pure gasoline to a 20% ethanol blend reduces carbon monoxide emissions by about 40%.
That's massive.
It is. It also drastically cuts down on particulate matter, the microscopic black soot that forms urban smog.
Because that extra oxygen ensures more of the carbon actually burns, rather than clumping together into soot.
Exactly.
But let's look at the flip side of that latent heat mechanism. The sweating engine is great when you're cruising down the interstate at operating temperature. But what is happening on a freezing morning in January when you first turn the key, the metal of the engine block is ice cold.
And that cold start is where the high latent heat of vaporization becomes a severe liability?
Yeah.
Yeah. At low cylinder wall temperatures, the ethanol-gasoline mixture doesn't have enough ambient heat to vaporize completely. Instead of forming a nice combustible mist, it stays in a liquid phase.
So it just pools up.
Right. It pools on the cold metal surfaces of the intake valves and cylinder walls. The combustion becomes wildly inefficient.
What happens to the exhaust then?
Well, instead of burning cleanly into carbon dioxide and water, the incomplete combustion spits out partially oxidized chemicals called aldehydes. Specifically, there is a massive spike in formaldehyde.
Formaldehyde, the exact same toxic carcinogenic chemical used in biology labs and embalming fluid.
The very same. The diagnostic testing shows a consistent, unavoidable trade-off. You get less benzene and less soot, but you get a dangerous spike in formaldehyde, especially during those critical first few minutes of a cold start.
That is definitely the hide side of the fuel.
And the paradox goes even further regarding temperature. Under heavy engine loads, ethanol makes the flame front burn much faster.
Okay, and why is that bad?
Because this faster, hotter, localized flame creates the perfect thermodynamic conditions for nitrogen and oxygen, which are normally inert in the air we breathe, to bond together.
Which produces nitrogen oxides, or novulox.
Mm-hmm.
So the fuel lowers overall engine temperatures by sweating, but the actual flame itself is so fast and aggressive that it fuses atmospheric nitrogen, spiking NOx emissions by up to 50 to 100% in certain conditions.
Right.
It's a literal chemical trade-off, molecule for molecule.
It really is. And if that's what it's doing to the air, we have to look at the physical hardware next.
Right. If ethanol is fundamentally altering the thermodynamic environment of the explosion, what is this highly oxygenated alcohol doing to the physical architecture of the fuel system before it even reaches the cylinder?
To figure that out, materials scientists rely on a technique called electrochemical impedance spectroscopy, or EIS.
Okay.
They use this on the metals and plastics that make up our fuel tanks, lines, and pumps.
Let's demystify EIS for a second. Spectroscopy usually involves light, but this is about electrical impedance, right? How does that reveal what the fuel is doing to the metal?
Instead of looking for visible rust, EIS runs a tiny, alternating electrical current through the metal sample while it's submerged in the ethanol blend.
Oh, interesting.
Yeah, as the chemical environment begins to interact with the metal on a microscopic level, even before there is any visible damage, the electrical resistance or impedance of the surface changes.
So it allows scientists to map the corrosion process at the atomic level in real time.
Exactly.
And what do those real-time electrical maps show when you soak engine parts in intermediate blends like E30 or E85?
Complete structural degradation.
Seriously.
Yeah.
Yeah.
The EIS studies revealed that these blends rapidly chew through copper and carbon steel. Ethanol is inherently more conductive than gasoline.
Right, because of the molecular structure.
And if it oxidizes even slightly, it forms organic acids like acetic acid. It essentially turns the fuel system into a weak battery, acting as an electrolyte that dissolves the carbon steel.
Wow. Does anything survive?
Stainless steel generally survives, but the cheaper metals used in older vehicles are destroyed.
If it's acting as an acidic electrolyte dissolving steel, I have to imagine it's an absolute nightmare for the softer materials. You know, the rubber seals, the gaskets, and the plastic fuel lines.
The elastomers fare even worse. Fuel system plastics absorb the ethanol molecules, but it's not like a kitchen sponge soaking up water.
Okay, how so?
The ethanol actually penetrates the polymer chains.
It sounds more like a dry wooden door swelling up in the frame during a humid summer. The moisture physically alters the structure of the material.
That's a highly accurate way to visualize it. The plastic swells, losing its tensile strength and becoming dangerously soft.
That sounds like a disaster waiting to happen.
It is, but the true catastrophic failure happens when the fuel system dries out. Ethanol is a powerful solvent. When it evaporates, it doesn't leave empty-handed.
Wait, what is the take with it?
It extracts the plasticizers. Those are the specific chemicals engineered into the plastic to keep it flexible. Yeah, so when the part dries, it shrinks significantly below its original size. It becomes rigid, brittle, and fractures under pressure. Suddenly, your high-pressure fuel line is leaking.
That brings us to the final piece of the hardware puzzle, phase separation. We know ethanol is hydrophilic, right? It readily forms hydrogen bonds with water, pulling moisture right out of the humid atmosphere into the gas tank.
Yes. Now, in pure gasoline, water is an enemy, but it's easily managed. Water and gasoline don't mix, so the water just sinks to the bottom of the tank where it can be filtered out.
But ethanol is different.
Right. Ethanol actively grabs that water and holds it in suspension throughout the fuel. Up to a certain point, the engine can actually just burn that tiny bit of suspended water.
Okay, but there's a limit.
Exactly. Temperature dictates how much water the ethanol can hold.
So when the temperature drops, say, transitioning from a warm autumn to a freezing winter night at around 0 degrees Celsius, the thermodynamic properties shift.
Drastically. At cold temperatures, the ethanol's solubility limit plummets. The hydrogen bonds holding the mixture together fail.
And what happens?
In a matter of hours, the ethanol and water mixture physically separates from the gasoline. It drops out of suspension and falls to the bottom of the tank as a distinct, highly concentrated, highly acidic sludge.
That makes so much sense. We always blame the lawnmower or the vintage car for being old when it refuses to start in the spring.
Yeah.
But it's actually the fuel dismantling it from the inside.
Exactly.
The fuel literally stratified, and the engine's pickup tube is trying to drink a corrosive cocktail of water and acid instead of combustible gasoline. This is exactly why your lawnmower or older car won't start if you leave gas in it over the winter.
Exactly the case. That is phase separation in action, dissolving carburetors from the inside out.
This Jekyll and Hyde reality is fascinating on a micro level, but I want to zoom out for a second.
Sure.
If ethanol behaves with this level of extreme complexity inside a single engine, what happens when we mandate its use across an entire country's infrastructure? The scientific literature here moves away from combustion physics and into massive global life cycle assessments, or LCAs.
And this is where we find one of the most fiercely contested debates in modern science. It's the equivalent of life cycle greenhouse gas emissions. Does producing and burning ethanol actually save carbon compared to just pumping and refining crude oil?
I can see why this is so difficult to measure. Like, if you're growing corn, a stalk of corn pulls carbon dioxide out of the atmosphere to grow.
Right.
So theoretically, burning it should just be a neutral, closed loop. But you aren't just planting a seed by hand. You have diesel tractors, nitrogen fertilizers, massive fermentation plants. How do scientists even begin to calculate that net impact?
That is the crux of the life cycle assessment. Under the U.S. Renewable Fuel Standard, the RFS, the EPA is legally required to calculate these exact boundaries.
Okay, and what do they find?
Their baseline finding historically has been that typical cornstarch ethanol barely squeaked past a 20% greenhouse gas reduction threshold compared to a 2005 gasoline baseline.
I mean, a 20% reduction isn't nothing, but it's a long way from the green savior narrative of the 1970s.
The science, however, is heavily disputed. A recent 2025 industry-sponsored review by a group called EHNE published updated LCA models.
Okay.
Their argument is that farming efficiency has evolved dramatically. They point to precision agriculture using GPS-guided tractors that use less diesel,
That makes sense.
plus no-till farming practices that trap carbon in the soil, and modern biorefineries that capture their own biogas for energy. When they run those variables, their models show corn ethanol actually emits 46% less greenhouse gas than gasoline.
Wow, a 46% reduction fundamentally changes the math. That makes it a highly effective bridge fuel.
It does.
But the data points in a wildly different direction when we look at independent models, doesn't it?
It really does. A major independent study published in the Proceedings of the National Academy of Sciences, or PNAS, took a completely different approach.
What did they do differently?
They argued that simple carbon counting is inadequate. Instead, they mapped what are called spatially and temporally explicit life cycle inventories of air pollutants.
So they aren't just asking how much pollution is created, but where exactly it is blowing and when it's happening. How does that change the results?
It changes everything. The PNAS researchers tracked the ammonia volatilizing off nitrogen fertilizers in the Midwest during spring planting.
Oh, wow.
They tracked the diesel emissions from the heavy machinery and the particulate matter from the ethanol processing plants. They then fed all of that into complex chemical transport models and paired it with public health databases.
To see the human impact.
Right. They wanted to see if the localized pollution from growing the corn was drifting into populated areas and causing respiratory illnesses.
They mapped the collateral damage of the agricultural supply chain.
Precisely. And their conclusion was staggering. They found that when you monetize both the global climate impacts of the greenhouse gases and the localized air quality health damages, the hospital visits, the respiratory issues,
Yeah.
corn ethanol actually performs worse than conventional fossil gasoline.
Wait, worse. Just to be incredibly clear to you listening, we aren't endorsing any of these viewpoints. We are just looking at the stark contrasts in the scientific literature. I mean, from industry claims of 36% reductions to independent models showing net negative health impacts. It shows how incredibly complex life cycle modeling is.
It really does. It all comes down to where you draw the boundary of your experiment.
Yeah.
If you only count the tailpipe and the ethanol plant, it looks great.
Sure.
But if you count the nitrous oxide off-gassing from the fertilizer, which is roughly 300 times more potent than CO2 as a greenhouse gas, and you count the indirect land use changes, the math collapses.
Wait, indirect land use changes? Like what?
Well, if a farmer in Iowa plants corn for fuel instead of soybeans for food, the global food market responds. Prices rise, and a farmer in another country might clear native forests to plant those missing soybeans, releasing massive amounts of stored carbon.
Oh, wow. It brings up the massive structural societal impact. The literature points out that roughly 40% of all U.S. corn production goes to ethanol. That is a staggering amount of land, water, and agricultural chemical runoff, dedicated not to the food supply, but to feeding combustion engines.
It is the ultimate food versus fuel friction. While the ethanol industry undoubtedly provides energy security and vital economic support for rural communities, it creates a rigid baseline of demand that alters the entire global agricultural landscape.
We've gone from the microscopic electrical impedance of a corroding fuel line to the macroeconomics of global soybean markets. Let's bring this vast scientific journey all home. What are the key takeaways from this deep dive into ethanol?
Well, there are three critical takeaways. First, from a thermodynamic and chemical standpoint, ethanol is a brilliant octane booster. Its high latent heat of vaporization cools engines down and cuts major pollutants like carbon monoxide and soot.
But with a catch.
Right. It comes at the direct, unavoidable cost of increasing other emissions, specifically NOx and cold start aldehydes like formaldehyde.
The Jekyll and Hyde chemical paradox.
Exactly. Second, its physical properties, specifically its hydrophilic love for water and its aggressive solvent capabilities, make it highly destructive to legacy engine materials.
Like melting the plastics.
Yeah, it swells and strips plastics of their flexibility, electrochemically corrodes carbon steel, and is incredibly prone to wintertime phase separation.
And the third takeaway.
Its true environmental impact remains one of the most fiercely contested debates in modern science. Whether ethanol is a climate savior emitting 46% less carbon or a net negative public health hazard depends entirely on how your life cycle assessment model measures farming impacts, land use, and localized air quality data.
It's wild how the answer completely changes based on the framing.
It is. I think the broader insight here is about the nature of scientific inquiry itself. We desperately want science to give us a perfect silver bullet, right?
Always.
We want a fuel that is 100% clean with zero physical drawbacks. But reality simply doesn't work that way. Science is really about managing highly complex, often painful trade-offs within massive interconnected systems.
Yeah.
When you pull a lever to reduce urban smog in Los Angeles, you might inadvertently push a lever that increases fertilizer runoff into the Mississippi River.
It is the ultimate balancing act of variables, and it really makes you rethink that little yellow sticker at the gas pump. It's not just a warning for your lawnmower. It's a window into a century of engineering, agricultural policy, and molecular compromise. Which leaves me with this thought for you to mull over. If we as a society are struggling this much just to optimize a relatively simple plant-derived alcohol in our legacy gas tanks, how will we ever navigate the immense complexity of transitioning to entirely new, unproven paradigms like synthetic e-fuels or a global hydrogen economy?
The trade-offs in those future systems will be just as complex, if not more so. That is the next great puzzle for researchers to solve.
And we'll be right here to dissect those models and discoveries when they do. Thank you for joining us in Deep Dive Lab. If you enjoyed uncovering the hidden science behind the everyday world with us, please follow and subscribe for more stories. Until next time you're standing at the pump, give a little nod to the incredible, invisible chemistry happening right beneath your feet. Stay curious.